So this the last method we'll be learning in this course, finite element method, and like MOM, FEM also have 4 basic steps. We'll see one by one by taking examples today. The first step is very similar to your MOM. You do the discretization of the solution region, and so you actually discretize the solution region into a finite number of subregions or elements, and for every element or subregion, you also find a governing equation. What are these governing equation? We'll see it today. Once you do that for every element, then you assemble all the elements in the solution region, and you actually solve the resulting equation. So we'll see it, all these steps one by one today also, tomorrow also, and so on. So let's take one simple example here so that you understand what are these 4 steps of finite element method. Step is basically finite element discretization. So here, let's say this is the solution region in the XY plane. This is solution region in the XY plane. You actually want to find something for the solution region, some unknown function for this solution region. What is the first step? You actually discretize this unknown solution region where you want to find the unknown function into small elements. So in finite element method, usually you take triangular elements as a small elements. For example, this is one triangular element here. So this solution region you actually discretize in terms of triangular regions. So you have how many triangular regions here? This is the first one, second, third, fourth, and up to 9 triangular regions here. So in order to make your understanding very clear, I put a bracket sign here for the numbering for the triangular region, because we have 2 different numberings here, one for the node and one for the element. So the triangular elements are numbered as bracket 1, bracket 2, bracket 3, and so on. And these are the nodes. You have nodes also. These are called nodes. These nodes are actually shown by green color here, numbering here, 1, 2, 3, 4, up to, we have 10 nodes here. So there are 2 different notations here. One with the bracket is for the element number, and 1, 2, 3, 4 without the bracket is for the node number. So you discretize the unknown solution region into triangular elements, and that's the first step. This is called finite element discretization. Then the next step is we actually find an approximation of the potential within an element. So we have how many elements here? We have 9 elements here. For every element here, we find the solution for the potential. So once you have the solution for potential for every region, you actually find the solution for the whole region by actually summing the potential for every region. Let's say we have capital N elements, then you find out the potential for every element. So E is going from 1 to capital N. So that means we have N, capital N triangular elements here. We find the potential for every element, which are denoted by B, E, X, Y. We are in the XY plane. So potential in the XY plane for the element 1, 2, 3 up to capital N, you find all of them, and then you sum them up, then you'll get the solution, unknown potential. No? That's a user practice. I'll spend more time on all these things later on. So let us first try to understand the steps which are used in the finite element method first. So now when you actually find out the approximation of potential inside an element E, there are some polynomial approximation people usually use. For the triangular element, the function people use is a plus bx plus cy. And for the quadrilateral element, instead of triangular element, you can also have quadrilateral element. In that case, the function approximate potential function you use is a plus bx plus cy plus dxy. You have one extra term here, dxy. So where a, b, c are the unknown constant you are supposed to find. Here a, b, c, d is the unknown constant you have to find. X and y are the variable for x-axis and y-axis. So this constant a, b, c, d are to be determined. So let's say if I want to find the potential for the element E, for the triangular element, if I know A, B, and C, I know the function within that triangular element. Similarly, if I want to know the potential function inside a quadrilateral element, B, E, X, Y, then I need to know what is ABCD. Once I have ABCD, I know what is the function inside the quadrilateral element. And we assume that potential is outside the zero, outside the element. We just find out potential inside the every element and sum them up, then we get the solution. We also, this is called element governing equation. So let's take one simple example. Consider a triangular element shown in figure, this triangular element here. How do I find out this unknown constant A, B, C, D? So for the triangular element, I just have A, B, C. For the quadrilateral element, I have A, B, C, D. So let us see how to find out A, B, C for a triangular element. Once I have A, B, C, I can find out what potential function inside the triangular elements. So let's say BE1, BE2, BE3 are the voltage at node 1, 2, and 3. So B1, B2, B3 is the voltage at node 1, 2, and 3. Usually you actually number this node. So a triangular element will have 3 nodes, 1, 2, 3. You usually number this in the anti-clockwise direction. That is because when you number it in anti-clockwise direction, there will be no negative sign when you find out. So I'll discuss that later on. So assume that B1 is the voltage at the node 1, B2 is the voltage at node 2, B3 is the voltage at node 3. And node 1 is located at x1, y1, node 2 is located at x2, y2, and node 3 is located at x3, y3. So our purpose is to find out what is the approximate potential inside this element. We know what is, let's say we know what is B1, B2, B3. We want to find potential inside this triangular element. That's the usual procedure we do for the finite element method. So how do we do it? Let's see. Okay, we have this relation BEX comma Y is equal to A plus BX plus CY. We want to find ABC. So let's say BE1, BE2, and BE3 are known to us. It's already provided to us. Then how do I find BE1? BE1 is ABX1 plus CY1 because the location of this BE1 is at x1 and y1. BE2 is A plus BX2 plus CY2. BE3 is A plus BX3 plus CY3. So that's how you find it. So I put this in a triangular, in a matrix form, B1, B2, B3 equal to 1x1, y1, 1x2, y2, 1x3, y3, ABC. This is the relation we have here. We are having values of B1 and B2, B3 at node 1, 2, and 3. Node 1 is located at x1, y1, node 2 is located at x2, y2, and node 3 is located at x3, y3. So now I am interested in finding ABC. So if I want to find ABC, I actually take the inverse of this matrix and multiply with the B1, B2, B3. So that's what I am doing exactly here. I take the inverse of this matrix, multiply with B1, B2, B3. So when I take the inverse of that matrix, I can easily find out from the linear algebra. If I want to take the inverse of a matrix, something like this, then I can always find it as 1 by 2a, this matrix here. So this matrix here, and what is A? A is the area of the triangular element. A is the area of the triangular element. Area of the triangular element can be found out as half of determinant of 1x1, y1, x2, y2, 1x3, y3. So this you can write it in this form. And you can simplify it. Area of this triangular element is half x2 minus x1, y3 minus y1 minus x3 minus x1, y2 minus y1. So these are standard formula in the linear algebra. So I can find out the area of triangular element. And 1 by 2a multiply with this, I get the inverse of the matrix, which we have discussed in the previous slide. So once I have this, I can find out what is ABC. So ABC is what I want to find. No? So if I have ABC, then I can find out what is the approximate function of the potential inside this triangular element. So I have told you we actually number these nodes in the counterclockwise direction. That is because A is positive. Area of the triangular element will be positive if we number the nodes in the counterclockwise direction. If we number it in the clockwise direction, then area of the triangular element will be negative, and we don't want that to happen. So finally, that we can express the approximate value of the potential inside the triangular element in this form. Summation I going from 1 to 3, alpha I x comma y b y. The relation we have, so we have the value of ABC here. You substitute the value of ABC and find out what is A plus BX plus CY. Then you can rearrange the term, and you can rearrange the term in this form as alpha I x comma y b y. So alpha 1, you can see alpha alpha 1 is dependent on x variable or as well as y variable. So this alpha 1, alpha 2 and alpha 3 are actually called shape functions. We have actually found out the value of ABC from the previous slide. Then we can rearrange the term and write the approximate value of the potential inside the element E, triangular element E, in the form like this: summation I going from 1 to 3 alpha I x comma y BEI. BEI is usually known to us. There is a voltage at the nodes 1, 2 and 3. Alpha I is actually a function of x and y. So now we can find out the potential inside the triangular element E. This is actually a little bit different from what we have for the FTDD. In the FTDD, what you do, you find out the fill at a particular location inside the grid. But here is something else. We are actually finding the fields inside the triangular element, which is a subsection of the solution space. You divide the solution space into small triangular elements. You find the potential inside the triangular element. But in FTDD, what we do is we subsection the solution space into small subsections, and we actually find out the value of the electric field at the center of the subsection at one particular point. But here we are finding it everywhere inside the triangular element. So that's a major difference. Because of that, FEM is also very accurate method, which will give you very accurate results also. Alpha i's are called the interpolation function or element shape functions, and this alpha I has a very good property, which is called alpha I equal to 1 when I is equal to j, and 0 when I not equal to j. So this will be very clear from this diagram here. If I draw this alpha I functions, alpha 1, alpha 2 and alpha 3, what I can observe is alpha 1 is having a value of 1 here, and 0 here at 2 and 3 node. It is having a value of 1 at node 1, and it is having a value of 0 at node 2 and 3. Similarly, alpha 2 is having a value of 1 at node 2, and at the remaining 1 and 3 nodes is having a value of 0. Alpha 3 is having a value of 1 at the node 3, and it is having a value of zeros at the node 1 and 2. So that is the property of this shape function we have considered. And when you sum all this shape function for every node, since here this is 1, but this is 0, 0, when you sum them up, it becomes 1. Here this is 1, then others are 0, then it becomes 1 again. Here this is 1, but others are 0. So that is what mathematically, when you write it, I going from 1 to 3 alpha I x comma y is equal to 1. So that is about the approximation of potential inside the triangular element. There is something called function, and I'll define all these terms later on. We'll just try to see what are the steps of finite element methods at the beginning. Then later on, I'll define all these terms. What do you mean by functional? All this? I will do it. I will spend time on this. But let us try to understand what are the steps, basic steps of finite element method first. The functional corresponding to the Laplace equation. This is the Laplace equation, del square B is equal to 0. And the functional for that is energy, W, energy per unit length, half epsilon E squared ds, half epsilon E. Electric field can be expressed in terms of electric potential as gradient of potential square. So the functional for this Laplace equation we are trying to solve is of the form half epsilon E squared ds. So this is the energy per unit length associated with the every element. So now this expression here, you have del BE here. So del BE, you can find out del BE when you take gradient of the potential function, approximate potential function. This gradient, you know what is BE? BE is summation I going from 1 to 3 BEI alpha I. But BEI is the potential we have already known at the nodes. This is a constant, but alpha I, as I have told you before, it was a function of x and y. So del will not operate on BEY because it's a constant, but del will operate on alpha I. Alpha I is a function of x and y. This is the expression you have for BE. BE is basically summation I going from 1 to 3 alpha I x comma y BEI. So when del operate on this BE, it will operate only on the shape functions. It will not operate on the BEI because this is a constant. So let us write down the functional WE. WE, you have del of BE. So WE is what? W is half epsilon summation epsilon del BE squared ds. So I can express this in this form here. Half summation going from 1 to I going from 1 to 3, j going from 1 to 3, epsilon BEI, BJ. Then this del is operating on alpha I and alpha j. So integration del alpha I dot product with del alpha j ds. So this term here inside the third bracket, people usually call this as coupling coefficients. Bi, Bj, these are all constant. Epsilon is also a material parameter, is a constant. We have a double summation here. The only thing which is changing with respect to x and y is this term here, this del alpha I and alpha j. After you do integration over ds, then what you are getting is called the coupling coefficient between element I and not I and j. So del alpha I dot product with del alpha j ds. This coupling coefficient is one of the major thing we'll be calculating in the finite element methods. So after you substituting Cij of this term here inside the third bracket, then what you can write is this functional W is equal to half summation I going from 1 to 3, j going from 1 to 3, epsilon Bi Cij for the element E Bij. So one of the measure work in the finite element method is to find this coupling coefficient. So finally in matrix form you can write W is equal to half epsilon Be transpose Ce then Be here, where your Be here, because we have considered one triangular element, it will have only three nodes 1, 2, 3. So Be will have B1, B2, B3. So the coupling matrix, see this is a triangular element. We consider how many nodes are there. 1, 2, 3 nodes are there. So you find out coupling coefficient from 1, 2, 1, 3, or let's say 2, 1, 2, 3, or 3, 1, 3, 2. So you'll have 9 elements here. So the coupling coefficient matrix, or people sometimes call this as stiffness matrix for the element E, can be calculated like this: C11, C12, C13, C21, C22, C23, C31, C32, C33. There will be 9 elements here. So for one triangular element, we need to calculate 9 coupling coefficients. So how do you do that? Let's see. That is from the definition. No, what is the definition? Definition is this: Cij is defined as integration del of, for example, if I want to find C12, then it is integration of del alpha 1 dot product with del alpha 2 ds. We have the expression for alpha 1 and alpha 2 in one of the previous slide. It was dependent on both x and y. So you do del of that. Finally, what you are getting is this. So these are actually independent of x and y. So that after you do del of alpha a dot product with del of alpha 2, whatever you are getting here, these are independent of x and y. So you can take it outside the integration. The integration simply remains as ds here. So when you integrate the triangular element over the surface area of the triangular element, you get the area of the triangular element. So this will become a. This a and this a square will cancel out. So what you have is 1 by 4a, this function here. So this is your coupling coefficient between node 1 and 2. So if you calculate the coupling coefficient from node 2 to 1, it will be same because nodes are just interchange. So coupling coefficient 1, 2 and 2, 1 will be same. So you can find it out also and verify it. Instead of finding del of alpha 1 dot product with del alpha 2, you have to find out del of alpha 2 dot product with del of alpha 1 ds. So you'll get the same value here. C12 is equal to C21. Similarly, if you want to find out the off diagonal element C13, you can also find out integration of del of alpha 1 dot product with del of alpha 2 ds. And similarly, C31 will be integration of del of alpha 3 dot product with del of alpha 1 ds. And if you want to find C23 and C32, what you do is you do the integration of del of alpha 2 dot product with del of alpha 3 ds. So you can find out all of them. This is what we have listed here. How about the, so this is about the off diagonal elements. So the final expression you can remember also, because in the, for example, you want to calculate quickly what is the stiffness matrix or coupling coefficient matrix. You don't have to do this derivation of all these formulas. So there's a one easy way of remembering all this formula for the off diagonal elements of the stiffness matrix. So basically, if you want to find C12E, here you have used node 1 and 2. What is the remaining vertex or node? It is 3. Then what you do? You find minus y3 minus y2, y3 minus y1, you plus minus. See, you first find out this term y3 minus y2, y3 minus y1 with a negative sign here. You add with the minus x3 minus x2, x3 minus x1. So what do you have? y3 minus y2, y3 minus y1, x3 minus x2, x3 minus x1. With a negative sign, you sum them up, divide it by 1 by 4a. You should be able to find out what is C12E. You don't have to do calculation. You can directly remember this formula. Similarly, for C13, if you want, what is the remaining vertex here? Remaining node here is 2. Then what do you do? y2 minus y3, y2 minus y1, x2 minus x3, x2 minus x1 with a negative sign, you sum them up, divide it by 1 by 4, multiply it by 1 by 4a, then you get the C13. Similarly, C23, what is the remaining vertex? 1. Then y1 minus y2, y1 minus y3, x1 minus x3, x1 minus x2. This would be x2 here. You with a negative sign, you sum them up, multiply by 1 by 4a, you should be able to get C23. So this is a very easy way of remembering this formula instead of calculating it every time. How about the diagonal elements? The diagonal elements would be calculated in a, so the formula to calculate diagonal elements will be slightly different here because C11 means what? You do integration of del of alpha 1 dot product with del of alpha 1 ds. So finally, when you do that, what do you get? So the formula for C11 is 1 by 4a y2 minus y3 whole square plus x2 minus x3 whole square. You can calculate it. But how do you remember it? C11, then find the remaining vertices. 1 here, then what are the remaining vertices? 2 and 3. So y2 minus y3 whole square plus x2 minus x3 whole square. You multiply it by 1 by 4a. Then you get C11. C22, what is the remaining vertex? 1 and 2, 1 and 3. So y3 minus 1, y1 whole square plus x3 minus x1 whole square multiplied by 1 by 4a. You get C22. This is how you remember the formulas. C33, what are the remaining vertex? 1 and 2. So y1 minus y2 whole square plus x1 minus x2 whole square multiplied by 1 by 4a. So finally C33 is this. So you don't have to calculate or derive the formula every time. You can just remember it, use the formula and find out the coupling or stiffness matrix. Okay, so that was for one particular triangular element, no? Any one particular triangular element E, but inside the solution space, we have many of them, triangular elements. We have to find the potential or stiffness matrix, then functional for every triangular element. But then how do you assemble all of them? So if I want to find the energy associated with the assemblage of elements, then what do? I sum all the energy for every triangular element. If I have capital N triangular elements, I sum the energy for every triangular element WE, W1, W2, W3, and up to W capital N. So this you can express in a very compact form, in the matrix form, half epsilon B transpose C. C is the coupling matrix, then B is the approximate voltage here. So here, the major difference here, since we have so many triangular elements here, this will not be just, B1, B2, B1, B2, B3. So we have many nodes here. Total number of nodes is small n, total number of triangular elements capital N. Then this B matrix will have B1, B2 up to B small n. So n is the number of nodes, total number of nodes in the solution space, and capital N is the number of elements. C is the overall or global coefficient matrix, which is the assemblage of individual element coefficient matrix. We find out the coefficient matrix for every individual elements, and we need to do something to find the global coefficient matrix. That also we'll discuss today. So let's see, take one simple example here. This is one solution region here. This is the solution region we are considering. We have divided this solution region into three triangular elements. This is triangular element 1 with the bracket here. This is triangular element 2, 2 with the bracket here. Triangular element 3. This is the triangular element with the 3 bracket here. So we want to find out the coupling coefficient matrix for every triangular element, and we want to also find out there are two kind of coupling coefficient matrix. One is the local one and is the global one. So for every local elements, we'll find out the local stiffness or coefficient matrix for triangular element 1, 2, and 3. Then we'll assemble all of them and find out something which is called global coefficient matrix. So how many nodes are there? We have 5 nodes here. 1, 2. So again, here there are two kinds of numbering here. inside the triangular element, what we have is 1, 2, 3, which is in an anti-clockwise direction. This is a local node numbering. We also have 1, 2, 3 here. This is local node numbering. Again, 1, 2, 3 here. This is local node numbering. We also have another node numbering, which is the global node numbering. 1, 2, 3, 4, 5. So we have 5 nodes total. So small n is 5 here. Capital N is 3 here because we have 3 triangular elements, and we have total nodes of 5, so small n is 5 here. So for this typical solution space, how do I do the finite element analysis? So global node numbering, number exterior to figure 1, 2, 3, 4, 5. Local node numbering always counterclockwise 1, 2, 3. We have 5 nodes, n is equal to 5, and we have 3 elements, n is equal to 3. So if we have 5 nodes, then how many elements will have 5 into 5, 25 elements here in the global coefficient matrix? We need to find all of this. There are some properties for the global coefficient matrix. First is that it is symmetric, Ci. And if Cij is 0, when there is no coupling exists between the node I and j. If node I and j are not connected, then Cij is 0. Because of this, Cij is equal to 0, the matrix coupling global coefficient matrix would be usually sparse. It will be a sparse matrix. Okay, so how do we find elements of the global coefficient matrix C? So let's see. This is the solution region. We have 3 triangular elements, 1, 2, 3. So now I want to find C11. This is outside the solution region. 1 outside, which is the global node number. I want to find C11. But what you see here is C11 for the global node number is actually also local node number for element 1, local node number 1 for element 1, and local node number 1 for the element 2 also. If I have the value of C11 for this element 2 and C11 for this element 1, then I just sum them up, then I get the C11 for this global node number. So C111 plus C112, if I sum them up, I get C11, which is what I want to find. This is the first element of the global coefficient matrix. So this one here for the global node number is actually 1, local node number 1 for the element 1 and element 2. Similarly, this global node number 2 is actually local node number 3 of the element 1. Similarly, this global node number 4 is the local element node number 2 of the element 1, and node number 3 of the element 2, and node number 3 of the element 3. That's how you find out. So let's see. If I want to find C22, C22 is only connected to the element 1, and this is the local node number 3. So C331, C331 would be the C22. If I want to find C44, now this C44 is the global node number C44. This is the global coefficient element of the global coefficient matrix, but then this is the local node number 2 of element 1, so C221. This is local node number 3 of the element 2, C332. And this is local node number 3 of the element 3, so C333. So you add all of them, then you'll get C44. Okay. That's what, let's say if I want to find C14, 1 global node number and 4 global node number, how do I find? So what you are observing is that this this 1, 4 is connected to element 1 and element 2. So what is that? For example, you consider for the element 1, this C14 is basically C12 of the local node number. For the element 2, this is the C13 of the element 2. So if you want to find C14, you actually find C12 of 1 and C13 of 2. You sum them up, you get C14. Let's say if you want to find C23, C and 2 and 3 are not connected, C23 would become 0. That's how you find out. C14 is equal to, due to the symmetry, C41 It is basically C12 of 1 plus C13 of 2. You can see that C23, 2 and 3 nodes are not connected. C23 is equal to C32 is equal to 0. So now you can fill up all the matrix now, and you can see that whenever there is no connection between the nodes, you have zeros here. Because of this zeros, the global coefficient matrix is usually very sparse. Okay. How to find the global coefficient matrix. After that, what do? You solve the resulting equation. This is the last step in the finite element method. So in order to solve the resulting equation, as you know that this Laplace equation is satisfied when the total energy in the solution region is minimum. So if you want to find minimum of any function, what do? You differentiate that function with respect to the unknown variable and equate it to 0. That is usually what you do in differential calculus. There is a function w, I want to minimize it. I actually differentiate with respect to a known variable b1, b2 up to bn and equate it equal to 0. So I can write this in a very compact form, w by dvk equal to 0 when k is going from 1 to k small n. So let's see how do you do that differentiation. For example, you consider the example of 5 nodes. This was the example we have shown, 5 nodes. This is the example we have considered. Let's say if I want to find dw by b1 equal to 0, then what do? W is half epsilon b1, b2, b3, b4, b5. We have 5 nodes here. b1, b2, b3, b4, b5. We have 5 global nodes here. And because of that, we'll have 25 elements in the global coefficient matrix. We have already found out this global coefficient matrix. b1, b2, b3, b4, and b5 are the node potential. So this is the expression for the W. If I want to differentiate W with respect to B1, let us just find out what is W is equal to epsilon. I have already multiplied this matrix and this vector here. This is what I'm getting. So again, I multiply this with this. This is what I'm getting. W would be having expression of this form, half epsilon. One thing we need to notice here is that this first row and first column, this row and first column is actually dependent on by. So when I differentiate W with respect to b1, only this term would be differentiated. All other terms are independent of b1, so it will become 0. So only this green term here in the first row and first column will be differentiated. So when I differentiate W with respect to b1, this is what I'm getting. To C11 B1, C12 B2, C13 B3, C14 B4, C15 B5, then B2 C21, B3 C31, B4 C41, B5 C51. And you also know that C12 is equal to C21, C13 is equal to C31, and C14 is equal to C41, and C15 is equal to C51. So finally, you can sum all of them. You'll have a 2 times C11 B1 plus C12 B2 plus C13 B3 plus C14 B4 plus C15 B5 equal to 0. So this is the resulting equation we are getting. When I differentiate dw divided by bk, this leads to equation of the form summation I going from 1 to small n bi cik is equal to 0. This is one case we have observed here. When I differentiate w with respect to b1, if I differentiate w with respect to bk, I will have equation of this form here. N is the number of nodes in the matrix. Okay, so we can find out this b1, b2 up to bn now from this equation. Okay, so finding the solution, there are 2 methods. One is called iteration method, another is called band matrix method. So first method is iteration method. Now how do I find out? Suppose node 1 is a free node. Free node is basically a node in which the voltage is not prescribed. That means node in which your voltage is unknown. Some of the nodes will be having some voltage and it will be given to you at the beginning itself. So nodes are prescribed means the value of the voltage at the nodes are known to you. But some of the nodes, the value of the voltage is not known. Then this is called a free node, and this is what we are supposed to find. A free node is where the potential is unknown. So from this equation, if I want to find B1, and if I know B2, B3, B4, and B5, I can easily find out B1 is minus C12, B2 plus C13, B3 plus C14, B4 plus C15, B5 divided by C11. So I can write this in a very compact form, minus 1 by C11 summation I going from 2 to 5 C1I Pi. This is how I find out this free node value if I know the value of the voltage at the remaining nodes. So I can write in a very general form for any node k in a mesh with n nodes. We have bk is equal to minus 1 by ck summation I going from 1 to n, I not equal to k cky bk cky bi. This is the equation from which we can find out the free node voltage. Okay, I think maybe I should stop here. Or okay. So you also know that CKI is 0 if node K is not directly connected to I. So nodes which are directly linked to node K contribute to BK in the above equation. If there is no connection between the node K and I want to find BK, then their node will not have any contribution. So only those nodes are connected to the node K would be contributing to this equation here. If CKI is 0, then there won't be any contribution from this node. So at the starting, this is an iterative method. So what is the initial value you should be taking? Iteration process start by assigning the potential of the fixed node equal to 0 or to the average potential. So what is the initial value of potential you take for the iteration? Usually it's 0 or the average potential. Average potential is basically half Bmin, Bmax. Bmin and Bmax are the maximum minimum values of the fixed node. So iteration start with the assigning of your unknown voltage at the nodes with 0 or the average potential. From there you can do the iteration by using this formula here. You should be able to find out all the nodes voltage. Once you have the nodes voltage, you can find out what is the approximate solution of the voltage in the unknown region space. I think we should stop here. If you want to discuss, we can discuss.